Hello everyone, welcome to Lecture 7, and in this lecture we will cover the continuous uniform and normal random variables. So we will start with the uniform distribution, and if you remember from the discrete case, the uniform distribution means the random variables, or in other words, each values of random variables will be equally likely. And that will be in the case of some interval, right? If you remember from the discrete case, we have some interval like that. Let's say this is A and B, and any single integer between this range will have the same probability, which is P, right? So this is that was the uniform discrete distribution. So same thing will happen in the case of the continuous uniform distribution. That's mean the two subintervals of A, B of the same length will have the same probability. What I mean, if let's say this is a continuous uniform distribution, and that's mean the X can take any value between A and B, and let's say this is the point C, and these two length is equal. Okay, so that's mean the probability of this part, the area in other words, will be equal to probability of this part. Okay, so that is actually the same manner with the discrete uniform distribution. So in the discrete case, the PMF was constant for all possible values, and we have here the same manner, the probability will be same. That means it will not change, okay? And here the PDF is constant for all possible values, as we said. That means the PMF of X will be some C, like this value will be C, if X ranges between A and B, and it will be 0 otherwise. So that means the PMF will be valid only within this range, okay? So the value of C, the probability, can be determined by using the normalization property. How? First, try to understand the logic of that piece of information. So what it says the value of C can be determined by using the normalization property. What was the normalization property? That's mean the probability of omega will be 1, right? In other words, if we use this piece of information for this one, the area of this part will be the 1, okay? How can I do that? If you remember that, so the accumulating all possible probabilities will give us 1, okay? So integration of C, which corresponds to this one, integration of the C over the domain of from A to B will be equal to 1, okay? So if we integrate this term, that will be C times X from the definite integral from A to B, right? So because here, which is actually C times X, okay? So this will give us the C times B minus C times A, and that will be equal to 1, right? In other words, I can write C as 1 over B minus A. So that's mean which is 1 over B minus A for some constant C. So when A is 0 and B is 1, the distribution is called the standard uniform distribution, and we will give the details of the standard uniform distribution and how we can use that standard uniform distribution to mimic the other kind of uniform distribution, okay? So just keep this in mind. If the X varies between 0 and 1, so we will define that as a standard uniform distribution. So here we found the C as 1 over B minus A, right? Inherently, we can reveal this value like that. This is A and this is B, right? So I know that the area of this region is 1, and the length of this rectangular is B minus A, and let's say the height is C. So I can simply say that 1 minus, B minus A times C will be equal to 1, right? This is the area of rectangle. And we can reveal the C as 1 over B minus A. Okay, so the question is, can we compute the CDF of that kind of distribution? So until X equal to A, no probability is accumulated, right? Because when I say before, the PMF is valid only within that range. That means the probability will be 0 until the point A, and there will be a jump. This will correspond to PMF, and if that is greater than 1, the probability again will not change, okay? Because the probability, actually that can be again 0, okay? Or we can say it will be same, like 1. Let's say that's 1. And the probability will not change. So the PMF will not be valid if the random variables is not within that range, which is here is B. So if you remember from the previous class, previous lecture, if you integrate the PMF for all possible values, we will get the CDF, right? If you remember that, what we say, we can calculate the PDF or PMF by using each other. So let's look at, let's say the X is between the A and B, and the CDF, the f of X, will be equal to integration of f of X t, okay? We use t because not to cause any confusion. The X is just the limit, and t is the variables will take the values between that range. And also we will integrate this term with respect to the t within those limits. So what was the f of X? F of X, we just calculated here, 1 over B minus A, right? So actually we can write this part as 1 over E minus A times t to the 0, right? So that means the definite integration will be 1 over B minus A times t from A to X. So the lower limit will be A and the upper limit will be X. So if we do the required calculation here, that will be 1 over B minus A times X minus A, right? Because t will get the X and A, so this is constant. So it will be 1 divided by B minus A times X minus A. And that will give us X minus A divided by B minus A. So for all, for X will be, for X greater than or equal to B, we have all the probabilities, all the probability accumulated. What I mean, if X is less than A, that part, the left side of A, the probability will be 0. because the PMF is not valid. And if X between A and B and A is included, in this case, I can use that probability, that PMF to calculate the corresponding probability. And if X is greater than or equal to B, in that case, the probability will be 1. Okay. So you can simply check these two ones by using that one. Let's say the X is A minus 1. Okay, so it is a less than A. So what will be this part? This part will be a negative number, and that will be a positive number. So the results will be negative number, but the probability cannot be negative. So the PMF is not valid. For this one, if X will be greater than or equal to B, let's say, for example, the B plus 1, okay? And the B plus 1 minus X minus A divided by B minus A will be greater than 1. So the probability cannot be greater than 1. That's why we will keep it same as 1. So the PDF again will not be valid if the X is greater than B. So okay, let's look at the expected value of the uniform distribution. So this is the graph of uniform distribution, and we simply calculate the expected value. What I mean actually, let's imagine that if I choose the millions of points between this range, what will be the mean of that points? And the basic logic of the expected value is simply for the discrete case was the summation of X times PMF of X, right? So, but for the continuous case, the expected value will be the X times F of X, the integration of X times F of X, right? So instead of summation, we used integration. And instead of PMF, we used PDF. Okay, the F of X was 1 over B minus A, so it can go outside the integration. So the term will be 1 over B minus A times integration of X over the domain from A to B, okay? So the antiderivative of X, if you remember, which is X squared divided by 2, and the definite integration will be X squared divided by 2 from A to B. And if you do some algebra, you will end up with A plus B divided by 2. So we can conclude some points from these results. We can say that the PDF of uniform distribution is symmetric. So it will be here, and it will be exactly the middle point of that region. And also the center of gravity should be on the symmetry axis. So the area of this one and this one will be the same. So the expected value of X in a uniform distribution, or we can say expected value of X which has a uniform distribution with the parameter A and B will be the A plus B divided by 2. To calculate the variance, let's first make the calculation for the second moment. That was the expected value of X squared, and that will be the integration of X squared times F of X over the domain from A to B. So we can do the same thing. This one is constant, and which is 1 over B minus A. That's not the base on X, so that we can take that 1 over B minus A outside of the integration, and we will stay with the X squared, the integration of X squared from A to B. So the antiderivative of the x squared is x cubed divided by 3. And that will be the final the final one will be 1 over b minus a times x cubed divided by 3 from a to b, definite integration. So, and if we do the required calculation, that would be 1 over b minus a times. First, put the b into the x. That will be b cubed divided by 3 minus a cubed divided by 3. So I can rewrite this part as the b cubed minus a cubed and divided by 3. So I can open this part as b minus a, okay, times b squared times ab times a squared divided by 3. So these two guys will cancel each other, and I will end up with a squared plus a times b plus b squared divided by 3. So I know the expected value and the expected value of the second moment, so I can simply calculate the variance, right? What was the variance? The variance is expected value of x squared minus expected value of x squared. I know this guy, which is this one, and I know this guy we just calculated here, which is a plus b divided by 2, and if I square of it, that will be a plus b squared divided by 4. If you do some algebra, you will get b minus a squared divided by 12. So the variance of the uniform distribution is b minus a squared divided by 12. So this is how we can calculate the variance of the uniform distribution. So if you remember from the previous slides, we say that if a is 0 and b is 1, which is called the standard uniform. But why? Because you can obtain any uniform random variable with a linear transformation of a standard uniform random variable. Let's say the x has a uniform distribution with the parameter 0 and 1. Okay, and let's say consider a new random variable y that can be written as b minus a times x plus a, and now we will have y has a uniform distribution with the parameter a and b. So that can be a little bit confusing, but let me clear it. Let's say we have x. X is this distribution, okay? 0 and 1. What we call this one, which is standard uniform distribution, okay? Now, which is x. Now, let's y has a uniform distribution with the parameters 5 and 10. Okay, let's graph that distribution. That will be something like that, which will be between 5 and 10. Okay, how can I rewrite this part as by using the x1? So the 5 is a, 10 is b, right? What I am given that the y is equal to this one, the b minus a times x plus a. Let's do that. The b minus a, 10 minus 5 times x, and plus a, which is 5. So this is y is equal to 5x plus 5. So we just a simple linear transformation, meaning that to get this kind of uniform distribution, we can multiply the standard uniform distribution by 5 and we can add 5. Okay, so this is a kind of transformation. But how that works? Let's say the x can take the values between 0 and 1, right? Let's say the x is equal to 0. In this case, the y will be 5 times 0 plus 5. That will be the 5. So this point exactly corresponds to this point. So the x, let's say, is 1. And in this case, that will be 5 times 1 plus 5. That will be 10. So this point corresponds to this point. So any point here, let's say, which is 0.5, okay, 0.5, which is exactly the middle of the range, this range, and we expect that the corresponding points in the graph of y should be the center of the range, right? Center of this range. So y in this case will be 5 times 0.5 plus 5, that will be the 7.5, right? So this 7.5. 0.5 is actually corresponds to this one. So this is exactly the center of this range. So this is how we can use the standard uniform distribution to find or to reflect any uniform distribution. Okay. If you mathematically prove that one, let's say let's complete the CDF of y. So the CDF of y actually will be equal to probability of y will be less than or equal to some y values, right? And that will be equal to, so instead of y, we can write, remember that 1 minus b minus a times x plus a. And we can replace this term with y, and it will be the probability of b minus a times x plus a will be less than or equal to 1. And if we subtract a from both sides and divide both sides to the b minus a, we will get the probability of x will be less than or equal to y minus a divided by b minus a. And this is actually equivalent to CDF of y minus a divided by b minus a, right? So let's write this term in this way by using the standard uniform distribution definition. First, remember that one. The CDF of the uniform distribution, the standard uniform distribution in this template, that's mean if x is less than the lower limit, the probability will be 0, right? This part. And if x greater than or equal to the upper limit, the probability will be 1. And if x greater than or equal to the lower limit and less than the upper limit, the corresponding probability will be x minus a divided by b minus a. So use the same strategy here. If let's think that this is our x in the standard uniform distribution definition, okay? So if x mean y minus a divided by b minus a less than the lower limit, the probability will be 0. If our new x, the y minus a divided by b minus a greater than or equal to upper limit, the corresponding probability will be 1. And if the new x, the y minus a divided by b minus a greater than or equal to the lower limit and less than the upper limit, the corresponding probability will be the x minus a will be 0 here, and x is 1, y minus a divided by b minus a divided by b minus a, that will be the 1 in this example. So the corresponding probability will be y minus a divided by b minus a. So let me write clearly. So that will be much better. Y1 minus c. Okay. But we can rewrite this part. Actually, this condition is same as this one, right? Y less than a, because if y is less than a, uh, this inequality will be satisfied because this part will be negative number and this part will be the positive. The results will be the positive, the negative. So, and also, let's write this condition as this one. If y is greater than or equal to b, we will satisfy this condition, right? Because if y is greater than or equal to b, this term will be greater than or equal to 1. So we will satisfy this condition as well. So we can rewrite this part as y is greater than or equal to b. And the other one is simple. The y will be greater than or equal to a and will be less than b. If y is a, if y is a, that will be the 0, I think, yeah, and this will be the 0. And if that is less than b, we will also satisfy this condition because this part will be less than or equal to 1. For example, if y is b minus 1, let's write this equality here. I mean, instead of y, let's write b minus 1. That will be this part. B minus 1 minus a divided by b minus a. So that will be less than 1. So instead of these conditions, we can write these conditions, and this will be the PDF of the y. CDF of the y. Okay, so this is the end of part 1, and we will continue with part 2, and we will discover the normal distribution.